We're starting into the dynamic section of the unit, meaning we're going to start looking at the forces that control things. And this is a review of grade 11 physics largely, but if you didn't have it, it's quite easy to teach you this section. We're going to be looking at Newton's law. There are three of them, but the one we're really going to focus on right now is the mechanics of using the law of forces. In metric, there are 7 fundamental units: meters, kilograms, and seconds. So a short form for metric is MKS. We can measure distance, mass, and time. There are actually only 4 more fundamental units: temperature, electric current, brightness of light, called candela, and moles, which you study in chemistry. And moles are the most ludicrous short form ever. To shorten mole, you write it mole. That's really a lot easier, isn't it? Derived units are built from combinations of those fundamental units. The most common derived units that you learned first in life were area, volume, and speed. Speed, meters per second. Those have combined 2 other ones. Density, kilograms per cubic meter, grams per cubic centimeter. You've combined 2 other ones. So this was your first taste at derived units in high school. But many derived units get quite complicated, and as a result, we start nicknaming them. In grade 9, I teach power, which is joules per second. Well, joules of energy per second get nicknamed a watt. This has the unfortunate consequence of hiding a rate. Students think a watt is a total amount of energy, like 5 loaves of bread, when really it's saying like 5 loaves of bread per day. So we're going to start seeing derived units that are given names, and then you have to convert them back to fundamental units if you need some more advanced stuff. The nice thing is I'll always tell you what these units are. So here's our very first one. Newton's law is often written this way: force is mass times acceleration. This means the push you gave an object of mass m to get a certain acceleration. You take the acceleration, you multiply it by the mass, and this is going to tell you the force you applied. Now, what would force be measured in? If I use square brackets, we're now talking about the dimensions only. And the dimensions of mass are kilograms. The dimensions of acceleration are meters per second squared. This means that the units of force are kilograms meters per second squared, which sounds really weird. So we call it a Newton. This triple bar means I'm telling you that this is the answer, or it's termed identically equal to. It just means there's no proof here. I'm telling you we're bundling this unit and calling it Newton. So let's just take a quick use of this equation. 2019 Honda Odyssey has a curb weight of 2,026 kilograms. It can accelerate to highway speed in 7.6 seconds. What force must the drivetrain exert to do this? Step 1, you knew several weeks ago. In order to calculate F equals ma, you need to get A. So acceleration is delta V over delta T. 30 meters a second. Why I have -1, I have no idea. It should be -0 because it came from rest. And I'm getting about 3.95 meters per second squared acceleration. And highway speed is around 30. So in 10 seconds, this would be at 39. That makes good sense. Okay. Notice I rounded highway speed to 30, not 27.7. Now we plug it into our formula. Force is m times a, and approximately, because I'm rounding, there's my acceleration rounded, my mass, and I get 8,000 newtons. If you wrote 8,000 kilograms meters per second squared, it's also the correct answer. So about 8,000 newtons of force are behind a vehicle to get it to highway speed in 7 seconds. So it's a lot. There's no way you can produce 8,000 newtons of force, because that's what a vehicle needed to get to highway speed in 7.6 seconds. That's a lot of force. Now, force happens to be a vector. It matters which way you are pushing. So this weightlifter is fighting a force of gravity that is pulling straight down on him. So when we want to calculate the force on the weightlifter, we must multiply the mass times the acceleration that should be appearing would he let it go. And that acceleration is 9.8 meters per second squared down. Notice I put the d in square brackets, and I even threw a vector sign over top. You really want to make sure that the direction is clearly stated and you don't muddle it up with the others. Now gravity, since it's a very constant acceleration, pulling straight down, we give it the name g. So g with an arrow on top is the vector version of gravity. That's what gravity will pull down. So what is this weightlifter fighting? If he picks up 100 kilograms and held it stationary above his head against gravity, the force he would need to provide would be force, it's m times a, it's 100 kilograms times the acceleration due to gravity, equals 980 kilograms meters per second squared. So this is 980 newtons down. So if you lifted 100 kilograms over your head, you would be subject to a downwards force of nearly 1,000 newtons. Is that a lot? I think for most of us, lifting 100 kilograms would be outside our range, but it is definitely within the range of training. So that again, 1,000 newtons would pancake most of us into the ground. Let's look at the whole mess here and see what we're dealing with. There's a number, there's a unit. There's a unit, there's a direction. The unit is being combined here. We still have a direction listed in there. So units, direction, and then these two are the same thing. They're a group of fundamental units that are given a name for convenience. And that triple equal sign is identity. It means I am telling you that this is the same thing. There is no difference between this here and that there. So to try to make it clear, I've left numbers in black, the units in blue, and the directions in red to make it clear that this is nothing scary. It's just a very complete answer. The key here, though, to really understand is that the force is not created from acceleration. Okay? Most people want to write Newton's law this way, but what this is really saying mathematically is that forces are a result of mass and acceleration. And that is not true. You didn't accelerate, and that'd be like saying, when I fell, I made gravity. No. Gravity is what made you start falling. It is the force acting on a mass that creates the observed acceleration. These two formulas are the same mathematically, but this formula shows the cause and effect. The cause, the effect. So once again, a force diluted by a mass it's acting on causes an acceleration. And that's really important to understand this. Forces cause the acceleration, and the acceleration is diluted down by the mass of the object. And as an interesting side note, if we look at it this way, forces are invisible, but they can be calculated. Mass and acceleration can be seen. So here's our cause, this is the effect, and this is the object. And if you keep that clear in your head, nothing in this unit is higher than grade 8 math. Next part, we're going to look at Dr. Dolittle and how it relates to this topic.